So now we're moving into section 4.3. Now let's remember where we've been. In 4.1, we learned about scatter diagrams and how powerful and important they are, how much they can show us about how two quantitative variables, relate to each other and how useful that is. Differences in scale, differences in correlation, and we learned what the correlation coefficient is, how to calculate it, what it shows us, all that good stuff. And then in but we also learned that just because you see a correlation, an association, doesn't mean that one causes the other, right? And then in 4.2, we learned, okay, well, if there's an association that's linear, which is what we're really interested in, then how do we find the line that's the best one? What does it mean to be the best one, i.e. that the errors are as small as they can be? And then how do you find it? And then once you found it, how do you use it? And how do you interpret the values of the slope, say, or the intercept? So we did all of that. And now that we're saying, okay, look, once you know how to find the line, there are some other things that we want to know, other good, useful indicators of things that are going on. So the first one is the coefficient of determination. Now, I got to give props to this. This little quote comes from a book called Statistics in Plain English, which it's actually a little bit not plain English if you don't know what you're looking at, but this is a great little topic right here that the author wrote about. So he said, when we want to know if two variables are correlated to each other, we are asking a more complex question. Are the variables in the scores on one variable somehow associated with the variations in the scores on the second variable? In other words, when you have two quantitative variables, does the up and down on one cause an up and downedness on the other one? Or, well, not cause, but are they related to each other? Okay. The coefficient of determination tells us how much of that variability, right, up and down spread in the scores of the one variable can be understood or explained by the scores of the other variable. Again, not caused by the other variable, just explained by. All right, so let's look at the heights and weights of 10 random people. We expect the heights to vary, i.e. some people are taller, some shorter. What's more, there's a total variation in height related to the variance of the heights, but I don't want to get into it, depicted by the circle on the left. So this is, if we have 10 people, this is the up and down we get in the heights. And I'm not talking about their actual heights. I'm just talking about the variation in their heights. And again, I have to give props on this whole page to the book. I'll put it up here, Statistics in Plain English, because that's where I got the idea for all of this. Okay. All right. So similarly, we expect weights to vary. Some people are heavier, some people are lighter. And so there's a total variation in weight. I'm not talking about the weights themselves. I'm talking about how far apart they are, right? So, some people are this, that, and the other, 100, 150, 200. I'm not interested in that. I'm interested in the variation from the mean, if you want to think of it that way. All right, if there's no correlation whatsoever between the two variables, then they're not going to overlap at all. Like height and IQ, and then it's going to be like, well, there's no relationship there at all. So here, something like that, right? And then that would be 0, right? Give you 0 for that. R squared would be 0, R would be 0. As a matter of fact, we saw graphs for those way back here, right there. Right there. So terrible, terrible R squared, everything's crappy. All right. Well, I got to find my graph again. I went to the other one so quickly. All right, so is this a realistic depiction for height and weight? Explain. So let me change this back to weight for a second. So is this really realistic that weight and height have no bearing on each other? And the answer to that, hopefully all of you know, is no, right? Height and weight do go together hand in hand, almost literally, right? Taller people have more mass in general. And so often way more. Even if you're skinny. I mean, you could have a skinny person who's 5 feet and a skinny person who's 7 feet. The skinny person who's 7 feet tall is going to weigh a lot more, right? It's just because they have more bones, literally, right? All right. If the two variables are related or correlated to each other, then there should be some kind of overlap, some kind of variation that they share that goes hand in hand with them. And that's what these overlap regions depict. All right, I'll pick it up right here next time.